Hi everyone, my name is Wardina Saffiyah Mohamad Zubir. I would like to present about introduction. So in this project, we focus on GPS, which stands for Global Positioning System. GPS is widely used in everyday life, such as from mobile apps and car navigation to agriculture and transportation. It works by using signals from satellites to define the user's location. However, GPS isn't always perfect. It can be affected by delays in the atmosphere, satellite timing errors, and signal reflection from buildings. These issues are especially common in a city environment. One common solution is the Kalman filter. It reduces noise and estimates position using previous GPS data. But it doesn't perform well when signal conditions change quickly. That's why we added machine learning. Machine learning can learn patterns from past GPS errors and help adjust the filter. The goal of this project is to build a GPS correction system in MATLAB by combining Kalman filtering and machine learning. In the end, we want to simulate and correct GPS error to improve accuracy in real-world conditions. Now, let's take a look at how GPS works and why it sometimes fails. GPS works based on trilateration. This means the receiver uses signal from at least 4 satellites to calculate your 3D position, such as latitude, longitude, and altitude. These signals are transmitted on 3 main frequencies, L1, L2, and L5. They use modulation technique like BPSK and QPSK and also encoded with unique PRN code so that signal from different satellites don't interfere with each other. So now, what causes GPS errors? First, atmospheric delays. Second, satellite clock drift. Tiny timing differences can cause big error. Third, multipath effect, which is signal reflect off surface like buildings, causing confusion in the receiver. And lastly, receiver noise. Internal hardware limitation can affect precision. This issue reduces GPS accuracy and reliability, which is why error correction methods like ours are important.
Introduction to GPS. The Global Positioning System, or GPS, is a satellite-based navigation system that provides users with position, velocity, and time anywhere on Earth by using signals from at least 4 satellites. How GPS works. GPS signals are transmitted on L1, L2, and L5 frequencies and use modulation like BPSK or QPSK. Each satellite send unique codes so signal don't interfere using a method called CDMA. GPS accuracy is affected by clock drift, atmospheric delays in the ionosphere and troposphere, and signal reflection from building, also known as multipath interference. More limitation. Receiver quality and satellite geometry also matter. Low-cost devices may introduce noise, and if satellites are too close together in the sky, position accuracy drops due to a high GDOP.
My name is Siti khadijah and my matrix number is B022220063, and I will be presenting the methodology part of our project. As we know, GPS is widely used for navigation. However, in areas with interference like cities or dense environments, it's often given inaccurate position. This happens due to signal delay, atmospheric condition, or reflection from the building. To solve this, we developed a system that combines Kalman filtering, which is a method for estimating accurate position, with machine learning, which helps the system learn and adapt to changing conditions. The goal is to make GPS data more accurate even in noisy environments. First, we created simulated GPS data in MATLAB. We introduced errors like ionospheric and tropospheric delays, multipath reflections, and satellite clock drift. After that, we cleaned the data by removing incomplete entries, smoothing out sudden jumps, and sensing the timestamps. Next, we model each type of error using basic formulas. For example, the atmospheric delay was calculated based on signal frequency, and multipath effects were added as delayed and weaker signals to reflect real-world behavior. Then, apply a Kalman filter. It works by predicting the next GPS position and correcting it based on new incoming data. This process helped reduce random noise and smooth the movement path. However, Kalman filters assume consistent noise, which is not always true in real situations. We integrated machine learning to improve it further by using key features such as signal-to-noise ratio, number of satellites, dilution of precision, and environment type. Then, test three machine learning models, which are KNN to classify signal quality, SVM to predict error levels, and decision tree to identify where big errors are likely to happen. These models help adjust the Kalman filter setting in real time, making it more responsive to changing GPS conditions. Next, test the full system in two simulated scenarios. The first one is open sky with minimal interference, or urban light with heaviness and reflection. In both cases, the hybrid model significantly improved accuracy. The corrected GPS path was much smoother and closely followed the expected route. In summary, this hybrid approach, developed entirely in MATLAB, shows that combining Kalman filtering with machine learning can enhance GPS accuracy. It is a promising solution for future applications, including mobile and real-time systems. Thank you.
A very good evening. So today I'll explain to you the coding for our project. So basically, this is the whole coding for the project. Firstly, CLC, clear and close all. So this is to basically to ensure that command window is clear. Then the second part, the T in space and through lag. This is when we simulate the true GPS for a moving object over an interval of 20 seconds divided into 150 samples. This path is not a simple straight line. It combines a linear progression with low and high frequency sinusoidal components using the expression through lag, this one. Then the design mimics real world movement scenarios. Okay, and then we go to the simulate realistic GPS errors. So basically, to emulate realistic GPS errors, five major error components are introduced. So firstly, ionospheric delay, tropospheric delay, satellite clock drift, and then multipath interference, and nonlinear noise. So each of these components is generated using different noise models to reflect how such error manifests in the GPS system. So for example, ionospheric and tropospheric error are modeled using Gaussian noise. Then satellite clock drift is simulated using a cumulative sum of small random variation. Multipath interference is modeled as a sinusoidal wave. And nonlinear noise is generated using a combination of random amplitude and sinusoidal phase variation. So these are added together with a true latitude to create a noisy GPS signal. Next is feature engineering for ML model, machine learning. So basically, with the noisy GPS data, we need to proceed to apply feature engineering for machine learning correction. So we construct a matrix of engineered features based on time, its square, then various sine and cosine functions of time. This feature aim to capture both linear and nonlinear patterns. So next one is linear regression model. So basically, we use linear regression model as the first stage correction mechanism. So MATLAB, FITLM, this one. Function is used to train the model using the engineered features. After training, the model predicts the error for each time step. Okay, so the machine learning step significantly reduce noise, especially which follows identifiable trends. Next, the adaptive Kalman filter. So the whole thing, further to refine the output, an adaptive Kalman filter is implemented. So this filter is designed to improve upon the regression model by dynamically adjusting itself based on the changing noise characteristic of the input signal. So the filter initializes with the starting error, then recursively updates its prediction and gain based on the observed movement. So in each iteration, the process noise is adjusted adaptively depending on the change in the character signal. Next, the validation matrix. So basically, this is following the Kalman filtering. We evaluate the performance of our model using Kalman matrix, mean square, mean absolute error, and maximum absolute error, and standard deviation. This matrix quantify the accuracy and consistency of the final output compared to the true path. Lower values across this matrix indicate a successful error mitigation strategy. Then, lastly, the plotting result. So basically, this is the coding to visualize the result using a plotting overlay and the true path. We visualize the results using a plot that overlays the true path. So the raw GPS path, the output from the machine learning model, and final character output from the Kalman filter. So without further ado, I will run the coding and then we can see the output. Okay. So basically, this is the output for the custom GPS area prevention. So this final graph generated from MATLAB implements offers a comprehensive visual. So basically, it represents the GPS model performance at each stage of error correction. So if I zoom this one, as you can see, the black solid line plots represent the true path, the actual trajectory. Then this reference path is essential for evaluating the effectiveness of the correction framework. So the red dashed line is a raw GPS, degraded GPS path due to a combination of simulated errors. Tropospheric delay, static cloud drift, multiple interference, and nonlinear environmental noise. So these error types are consistent. Then and that's it. So this is how the output after we run the coding. So to further enhance the output, an adaptive Kalman filter was applied to machine learning. Process follows the true path with minimal deviation. So this hybrid approach leverages the predictive power of machine learning and the smoothing capability of Kalman filtering. So in conclusion, this developed MATLAB-based hybrid GPS error correction model effectively satisfies the assessment criteria. So it successfully models and prevent major GPS error source. So for the blue line, the corrected line does a much better job for following the descent. Although it still carries slight fluctuation around the true path, it noticeably reduces the amplitude of deviation present in the raw GPS data. This shows that the machine learning model is successful learning the pattern of the error. So you can use machine learning, also the Kalman filtering to mitigate the problem of the error of a raw GPS. So that's it. Thank you.
So this is our conclusion part. Firstly, we built a system in MATLAB to improve GPS accuracy by combining machine learning and Kalman filtering. We used two methods. Firstly, machine learning. It predicts how far the GPS is from the real location. Second, Kalman filtering, which is it smooths the data and adjusts it in real time. Next, GPS signals are often inaccurate due to atmospheric delays, satellite timing issues, and signal reflection. We also test the system using simulated GPS data with different types of errors to see how well the correction works. We also gain valuable hands-on experience working with signal processing and machine learning in MATLAB. So, lastly, the final output was closer to the real path and error values like RMSE and MAE were much lower, showing better accuracy.